actually have the same learning goals yesterday. I can multiply polynomials. Now, the other thing that I would like you to do is make sure that you write the product in simplified form. And the other thing I like about Hayden and Company's answer for this one is they also put it in standard form. So when it can be put in standard form, when can polynomials be written in standard form? When there's only one, not one term, one variable. When there's only one variable involved, we can write it in standard form, and then we do it from greatest degree of each monomial term down to the least degree. So let's write this down. FOIL can only be used for binomial times binomial. Do not be fooled into thinking it's going to work just any old time you're multiplying polynomials. FOIL has 4 letters in it, but multiplying binomials has 4 multiplications in it. So if you want to make up your own acronym for 6 multiplications, you could try it and see if it would, help you out. So when we actually multiply our 2x minus 3 times 3x plus 4, can we use FOIL for this one? Yeah. Okay, let's do it. Go ahead. This is review from yesterday. Set up your FOIL and see what you get for a product of these binomials. So if you need to get out yesterday's notes to help you out, feel free to. Okay, I think you might be ready for me. What's the first product? What's the F product?
6x squared.
6x squared. From another voice, what's the O product? 8x. From another voice, what's the I product? Negative 9x. That was a few voices, but okay. And now from a different voice yet, what's the L product? Negative 12. What did I say will typically, but not always, happen when you're FOILing these binomials? What will typically, but not always?
The O and the I, you can add them.
Yeah, typically, and this is again, just typically, the O and the I step will become, they should turn out, their product should be like terms so that when you can combine them, you can add them together. No multiplying anymore. Now we've done all our multiplying. What we really have here now is the addition of 4 terms. So we are going to say 8x plus negative 9x is negative x, or negative 1x, right? Now we can say we have 6x squared minus x minus 12. There is our product. Did you get that? Is that what you guys got? Okay. Well, I'm going to teach you another method that I think, might be handy. It doesn't mean you have to use it. If this works for you, what Hayden was doing with all the arms, and he's just really doing distributive property here, taking each term and multiplying it by every other term. Every term has to be multiplied by from one of them has to be multiplied times the others in the other polynomial. So you have to make sure you cover all the multiplications. So I'm gonna go with a rectangle method as one way to help you maybe be successful with these. And first thing we're going to do is we're going to change this subtraction to add the opposite, just like I really did up above when I was FOILing also. And we're going to have a rectangle model this multiplication. One side of the rectangle is going to be the length, and the other is going to be the width. So this becomes the length of it. The 3x plus 4 becomes the width of it. And this will help us accomplish the 4 multiplications that we really need to do. So when we are going to multiply these, what we can do now is find the area of each of the smaller rectangles. Now we're not going to do any work in this one. I want your notes to be very clear how, like, kind of the process we used. So here we're just setting up our rectangle. Let's change it here to, or let's transfer it over to here. I'm going to call this our work rectangle, because what's really going to happen now is that rectangle has been, the big rectangle has been divided into 4 smaller rectangles. Each of those rectangles has its own width and its own length now. So the first one has a length and a width that can be multiplied times each other. Order does not matter when we're multiplying. So we show that 2x has to get multiplied times the 3x. This rectangle has dimensions of -3 times 3x. Again, remember, order does not matter in multiplication. So it is -3 long, 3x wide. How about the bottom left rectangle? What would its multiplication be? 4 times 2x.
4 times -3.
And 4 times -3. Now I want you to go up and I want you to compare and see. Were those the 4 multiplications that really ended up getting done in FOIL up there? Somewhere? 2x times 3x? 2x times 4? -3 times 3x? Yeah. 4 times -3. So the same multiplications end up getting done, just not using FOIL, but using the rectangle instead. And now let's find our products. 3x times 2x. Now today would be the day that I'm going to let you do it, like about showing the arranging on your paper that 3 gets multiplied times 2 and x gets multiplied times x. You should be ready to do that now. What's 3x times 2x? 6x squared. -3 times 3x. -9x. 4 times 2x. 8x. And 4 times -3. -12. Now, if the polynomials were written in standard form, the length and the width, those binomials were written in standard form, and it's kind of like all the terms of it were possibly, that could possibly be there or there, from least grades to least degree. What should typically happen, again, this is typical, what should typically happen is any like terms will typically line up on a diagonal. So what we really have here is 6x squared plus our -9x plus our 8x plus our -12. And do you see how the like terms line up on the diagonal? And we're going to bring those together and say we have a -1x, and then we're going to clean this up. 6x squared minus x minus 12. We get the same product as we did when we used FOIL. But here's the reason the rectangle method is handy. Because it isn't limited to just a binomial times a binomial. You could use it for a monomial times a monomial. You could use it for a monomial times a binomial. You could use it for a trinomial times a 5-term polynomial. You could use it for any multiplication of a polynomial. So let's go to the back side and do something that looks a lot like what I had you starting out with at the beginning of class. Okay, so we're going to use the rectangle method because we know FOIL isn't going to work for this one, right? Why isn't FOIL going to work for this one? Binomial times a trinomial. So the first thing I'm going to do is this. This is when it's kind of important that you make sure you understand that -5 really means a -5. We need a rectangle that has, dimensions of, x plus -5 and -3x squared plus x plus -4. So I really need a binomial, a 2 by 3, 2 times 3, because we're taking a binomial times a trinomial. So we're going to draw ourselves a rectangle that is a 2 by, whoopsie, that was not good. 2 by 3. So if I have 2 rows, I have to have 3 columns. So where's the binomial going to go? Across the top or down the side? Down the side. So x, -5. Our trinomial terms will go across the top. Okay, let's just show our work step. These are our notes. Let's make sure that we can tell what we did in our notes when we look back on testing. We are going to multiply. We're going to set up a multiplication for each rectangle. So x times -3x squared. X times x. Okay, you can fill in the other 4 multiplications on your own now. Show the multiplications, not the products. Show the multiplications. So we'll call that our work rectangle. Do you agree with all my multiplications? Let's go draw this rectangle again, so we can have we'll call this our product rectangle. You don't need the things across the top anymore. This is our product rectangle. So we're going to actually do the multiplying now and see what we get. So what's the product of the x times -3x squared? What would that be?
-3x cubed. 2/3.
To the third, right? Because this is to the first. 1 plus 2 is 3. Okay. I'm kind of sad that this is the part we're stuck on right now, and we can't multiply these monomials. X times -3x squared. No, we've been doing the last couple of days. Okay. Let's finish. Go ahead, finish filling it out. I can't hold your hand for everything. And let's note that I said on diagonals, you should oftentimes see like terms lined up. See them? So if you're going to shortcut it all, the shortcut would be, well, why don't you draw, like circles? They're not really true circles, but circles around those diagonals, and then you could say, I have -3x cubed plus, what would the sum of this one be? 15x squared plus x squared. 16x squared. Or you could write down -3x cubed plus x squared plus -4x plus 15x squared plus -5x plus 20. But here's what ends up happening. They get out of order, and then you're like, oh, now I got to reorder them. So this way, if we just do it as we're moving along, what do the x's combine to become? -9x. And the 20 doesn't have anything to be combined with, just like the -3x cubed did not have anything to be combined with. Now we can clean up our answer. -3x cubed plus 16x squared, feeling like it's in standard form so far, minus 9x, looking good, plus 20. Now, do you think you could be successful with this problem? You have maybe a strategy to use. Okay, I want you to get the next one set up. I want you to show the work rectangle only. Oh, I can't do that. Not gonna work very well. Now, our rectangles might not look exactly the same, but what do we have to each have? Either what would the dimensions be? Either a 2 by 3 or a 3 by 2. Not bad. 2 times 3 is the same as 3 times 2. 6. We have 6 multiplications that need to happen because we have a trinomial times a binomial. 3 times 2. So, get your multiplication set up, and this is your work rectangle only. Could you do it the other way? Is that what you asked?
Yeah,
Absolutely.
I did.
Okay, we'll see if we get the same answer. We should still have the same 6 multiplications, they just aren't going to look like maybe they're in the same order. And then we will move to our product rectangle. Don't be changing up your way you set up your rectangle after you've done your work rectangle. They need to stay the same. Okay, check to see if you have the same 6 products I ended up with. Somewhere in your rectangle you have those same 6 products. Catch my mistake if I made one. Y'all think I know what I'm doing? I got this? Okay, so remember what I said. Typically, but not always, diagonals will be like terms. In mine, I see some like terms right here. Are there like terms on the other diagonal? No. There won't always be, and I'll tell you why. Or can somebody tell me why they think there may not be any other diagonal like terms? Anybody think they know what might be the reason why I can't have 2 diagonals in this like terms? Okay, I guess I'll give it away. Because some of the terms are missing in these. We have cubes, but we don't have any squares. We have squares, but we don't have any x's. That's the reason why. So we're going to say, okay, I have 2x to the 5th. Don't have any other of those. What's the x cubed going to combine to become? Negative 7x to the 4th. To the 3rd. Since I can't combine anything else, right? What would I want to bring down next?
Plus 12x.
the 12x squared, because then it would be, I'd be getting it in standard form, wouldn't I? What's the next one bring down then? 3x, and then the negative 6. Okay. And now we'll clean this up. 2x to the 5th minus 7x cubed plus 12x squared plus 3x minus 6. Whew, that is quite an answer.
And then the other one is
You do the same answer? Awesome. Good to know there's 2 different ways you can set up the first one. Okay, any questions? Okay, then let's get to work.